Hello, everyone. Welcome back. Today we're diving deep into the nuts and bolts of plumbing systems, specifically looking at Division B of the National Plumbing Code. We're going to cover everything from how to handle suds pressure, yes, soap bubbles are a serious engineering problem, to calculating hydraulic loads for massive buildings. It's technical, but trust me, getting this right is what keeps our buildings safe and sanitary. Let's get started.
First up, let's talk about connections. You might think you can just hook a pipe in anywhere, but physics disagrees. When you have a vertical stock transitioning to a horizontal branch pipe in these turbulent zones, you're asking for blockages and backflow.
Now, here's a concept that always surprises people: suds pressure zones. It sounds funny, but modern high-efficiency detergents create suds that are surprisingly tough. These suds can actually disrupt the venting action in a multi-story building. The more turbulence you have in the pipe, the more suds you generate, and they can spread through the lower portions of the drainage system.
So how do we fight the suds? The material suggests a smart design fix. Connect the suds-producing stack, like the one from the laundry room, downstream of all other stacks. You also want to increase the size of the horizontal drain to let more air and water flow through, and use streamlined fittings, like Ys, to smooth out the flow. Less turbulence means fewer bubbles.
Moving on to organic solids, we're talking about things like garbage grinders and potato peelers. These machines chop waste into tiny particles that flow easily at first. The problem is, if you put these devices upstream of an interceptor, those tiny particles settle and can completely block it. It's a classic case of one solution causing another problem.
Then we have the nasty stuff: grease and hazardous waste. If you're discharging fats or oils, you likely need a grease interceptor. The code actually points to a specific handbook for sizing those. And for biohazardous or chemical waste, that's serious business. The treatment of corrosive waste is mandated by the code, but biohazards usually require specific engineering expertise outside standard plumbing rules.
Let's look at sinks, specifically trapping. You don't always need a separate trap for every single bowl. If you have a 2 or 3 compartment sink, you can use a continuous waste setup where they all share one trap. The key rule here is the developed length. The pipe from the fixture to the trap can't be longer than 1,200 millimeters. Keep it short to keep it flowing.
This logic applies to groups of fixtures too. You can have multiple floor drains or shower drains connecting to a single trap. It's efficient, but you have to watch your venting. Interestingly, if you replace a trap with an interceptor, that interceptor has to be vented exactly like the trap it replaced. You can't just swap them out and forget the airflow.
What about the water under the building, subsoil drainage? The code doesn't tell you how to lay the subsoil pipes themselves, but it does regulate how you connect them to the plumbing. You absolutely need a trap between the subsoil pipe and the sanitary system. You don't want sewer gases migrating back into the soil around your foundation.
Speaking of traps, let's talk about the main building trap. This is the big gatekeeper. It can be inside or outside in a manhole. Crucially, it needs a fresh air inlet, a pipe allowing air in, that's at least size NPS 4. And you need a clean out right there, because if this trap clogs, the whole building backs up.
Now, traps only work if they have water in them. If a floor drain sits unused, the water evaporates and the seal breaks. In a house, you can just dump a bucket of water in occasionally. But in commercial systems, or where there are pressure differences, we use trap seal primers, little devices that automatically drip water into the trap to keep that seal full.
Sometimes gravity isn't enough, and we need a sump pump. The setup here is specific. You need a union, a check valve to stop backflow, and a shutoff valve. And here's a critical sizing rule. If you don't have automatic float controls, your sump pit needs to be big enough to hold the entire maximum inflow expected in a 24-hour period. That is a massive tank.
If there's a risk of the public sewer backing up, what we call surcharge, you need protection. This is where backwater valves come in. You might put them on individual fixtures or on a whole branch. It's basically a one-way door for waste. If the city sewer pushes back, the valve slams shut and saves your basement. Island sinks are tricky because there's no wall to hide a vent stack in. So how do we vent them? We use a special loop method. The vent goes up as high as possible under the counter, then loops back down under the floor. It's a clever workaround, but it requires cleanouts because those loops are prone to clogging.
All right, let's get into the math. Hydraulic loads. We don't just measure water in liters, we use fixture units.
A fixture unit is a dimensionless factor that accounts for how much water a fixture uses, how long it runs, and how often it's used. Here's the catch. You cannot simply convert fixture units to liters per second directly. It's not a linear relationship.
Why isn't it linear? Because of simultaneous use. In a huge building with 1,000 toilets, they will never all flush at the exact same second. So doubling the fixtures doesn't double the peak flow. The code uses a complex curve to figure this out. But for continuous flow items, they give us a conversion factor, 31.7 fixture units per liter per second.
So how do you size a sanitary pipe? It's a 4-step process. First, add up the fixture units for normal stuff like toilets and sinks. Second, take any continuous flow, like a pump, measure it in liters per second, and multiply by 31.7 to get fixture units. Third, add those two numbers together. Finally, look up that total in the code tables to find your pipe size.
Storm drainage is different. Here we care about area and rain intensity. You take the area of the roof in square meters and multiply it by the local rainfall intensity from the building code appendix. That gives you a load in liters. If you have continuous flow into a storm drain, the conversion factor changes. It's 900 liters for every liter per second.
Now, the final boss level, combined sewers. This is where sanitary and stormwater mix. To size this pipe, you have to convert everything into liters. For the sanitary part, if the load is over 260 fixture units, you multiply by 9.1 to get liters. Then you add that to your stormwater liters. It's a bit of math gymnastics, but it ensures the pipe can handle the worst-case scenario.
Jumping right back into it, let's talk about rainfall intensities. If you're wondering where to find the specific climate data for rainfall in different cities, the code points us directly to Appendix C of Division B in the National Building Code.
There's a really handy conversion rule mentioned here for calculating hydraulic load. Basically, if you have 1 square meter of roof or paved surface and you get 1 millimeter of rain on it, that equals exactly 1 liter of water. It makes the math surprisingly straightforward.
Now, moving on to something a bit more technical, trapping floor drains. The code provides specific diagrams for how these should be connected, specifically looking at drain traps that are NPS 3 or larger.
The critical detail here is about the length of the fixture drain, labeled as A in the diagrams. The material specifies that this length must be at least 450 millimeters. But here's the catch. The fall or slope of that pipe section cannot exceed the size of the pipe itself.
Whether you are connecting to a building drain, a branch, or a stack, the configuration matters to prevent siphonage. The diagrams in the code, specifically figure A2.5.1.1.3, show us exactly how to route these to ensure the trap seal stays intact.
So just to wrap up this section, remember that 1 millimeter of rain on a square meter is 1 liter. Check Appendix C for your local rainfall stats, and keep those floor drain connections at least 450 millimeters long without sloping them too steeply. That covers the essentials.